Hello everyone, I am Saber from Italian Institute of Technology, and today I'm going to present you our recent work called PointView-GCN, 3D shape classification with multi-view point clouds, co-authored with Yiming and Alessio. 3D object classification can be defined as predicting the object class label in 3D environment. The problem of recognizing an object in 3D has gained increasing research attention since 3D data provides both 3D geometry and semantic information of the object, and it has an essential role in variant real-world applications such as autonomous driving, domestic robot, and virtual reality. But the question is that how to do 3D object classification? There exist variant ways to process 3D data for object classification using deep model, where the most common one are multi-view images, voxel, and point cloud data. However, point cloud data-based network gained a lot of attention in recent years because point cloud are simple, which helps to avoid the complexity of other data formats, and so they are easier to learn from. But existing methods, which are based on the point cloud data, first register point cloud by multi-view capturing, then they process complete point cloud data as the input of the network, which is not realistic in many real-world scenarios. On the other hand, existing multi-view methods mainly exploit images with the intention of encoding multi-view image feature. Differently, in our work, for the first time we process multi-view point cloud data directly for shape classification. Here is our overall pipeline of PointView-GCN, where we first capture multi-view partial point clouds by RGBD cameras which are virtually generated around the object. Then we fed each partial point clouds to the backbone network in order to learn and extract a feature from them. Finally, we apply multi-view graph convolutional network on a view graph to aggregate the extracted feature for shape classification. Here you can see our feature aggregation network, where we first construct the initial view graph G1 of n nodes, and each node is represented by the extracted shape feature from the backbone network corresponding to each single viewpoint cloud. Then we fed the initial view graph to Graph Convolutional Network in order to update the node's feature by considering its relationship with their neighborhood views and the relationship with the whole nodes in the view graph, followed by selective view sampling to select the nodes with the highest response to the softmax function. Finally, the Corsan view graph with its associated updated feature is fed to the next level of graph convolution. After each graph convolutional level, a max pooling performs on the updated feature to obtain the global shape feature. The final global shape feature is a concatenation of all pooled features at all levels. We also add one residual connection from the output of the first convolutional level to the last one to prevent from vanishing gradient. The training loss consists of two elements, global shape loss and selective view loss, where the global shape loss is a cross-entropy loss with a fully connected layer and softmax function. Selective view loss is the cross-entropy loss for the view selector necessary to evaluate if the selected view can recognize the shape object or not. Here I am going to explain your dataset generation pipeline. For the dataset rendering, we choose 3D patch representation of each object in order to account for self-occlusion. We then position a virtual RGBD camera at each view post for depth capturing. After that, we convert all acquired depth image to point cloud using camera extrinsic and intrinsic matrix. The reconstructed single view point cloud are often self-occluded due to the limited visibility of camera view. Following the dataset generation pipeline described in the previous slide, we generate the dataset under two view camera configurations, namely dodecahedral and hemispherical. For dodecahedral view configuration, we place 20 equally spaced viewpoints on the dodecahedron surface, and for hemispherical configuration, we place 12 cameras lying on the upper part of the dodecahedron surface. The hemispherical configuration is motivated by the fact that the viewpoints, which are located on the lower half of the dodecahedron surface, are mostly invisible in reality. We build 4 single viewpoint cloud datasets under 2 view configuration with self-occlusion on the top of the synthetic model net 40 and scan object NN, which address real-world object recognition challenges. Here you can visualize our self-occluded single-view dataset, which are generated on the top of model net 40 and scan object NN. We compare PointView-GCN against a range of the state-of-the-art method for shape classification. Regarding model net 40, PointView-GCN outperforms the best performing state-of-the-art method with 3D data, which is DGCNN, by 2%, while approaching View-GCN, which has access to multi-view image data with more fine-level details of an object. For a scan object NN, generally existing point cloud-based network performs worse on real-world self-occluded point cloud data compared to the synthetic dataset. With PointView-GCN, we can observe the consistent improvement in performance by about 6% comparing to the method fine-tuned with single viewpoint cloud data, while reaching comparable performance to the best performing methods, that is DGCNN, with a margin less than 1%. Here I am going to present you some additional experiments to justify our design choice. Firstly, we evaluate how the number of the GCN levels affects the classification accuracy with a 4 single-view dataset, as well as addition of the skip connection between the first and last layer with respect to our baseline. As you can see, with an increasing number of the GCN levels, the classification accuracy increases and saturates at the 4th level. We also notice that the skip connection helps to improve the classification accuracy by slight margins on all datasets. Next table shows the result of our method with a varying number of the input views gradually decreasing from 20 to 8. It can be observed that there is a marginal reduction in accuracy when we reduce the number of the input views from 20 to 12. However, the accuracy drops significantly when the number of the views are reduced to 8. Last but not least, we show the consistent capability of PointView-GCN for feature aggregation. With the weakest single-view shape feature, PointView-GCN increases the classification accuracy by 15%, while for the strongest single-view shape feature, there is still 5% improvement. Conclusions. We figure out that aggregating multi-view shape feature with a multi-level graph convolutional network produces more discriminative global shape feature compared to the shape feature learned from complete PCD. With our experiment, we show that such an improvement can be consistently obtained by 5%, regardless which feature extraction backbone is used. We also showed that the number of the GCN level has a direct impact on the feature aggregation performance, where the optimal is observed at the 4th level. As a future work, we will further investigate the fusion of multi-view image and shape features within the framework of our network to boost the 3D classification accuracy.